Excellent. Right. Well, welcome everybody to this evening's talk at the Astronomical Society of Edinburgh. Before Mark introduces our speaker for tonight, I'd like to welcome two new members. I don't know if Louise and Daniel are listening.
I can see Daniel on here.
Do you want to say hello, Daniel?
Hello.
Well, welcome to you.
I'm just in the middle of making some bread, so but what from you guys?
Fine. Perhaps the members like to unmute and welcome our new members in the usual way.
New member.
And hopefully before long we'll be able to meet. So our membership is now 114, which is probably the biggest it's been since about 1924 when we were formed. An incredibly good value, as I always say. And if you're interested in joining, our website is at the bottom, and full details are there, and you can join online. Okay, next slide, please, Mark. And just to mention some of the things that's on the agenda coming up. On Friday, we've got Jim Anderson, our own salty sea dog, who's going to talk to us about astronavigation for sailors. On Wednesday the 24th, we've got 3 scope and shed talks. Peter will have to explain what he means by a shed talk, but Tosh White, Mike McGovern and Peter Black will be talking then. On Friday the 26th, Dr. Bruce Vicker is giving one of his excellent talks about James Bradley and others, fact-checked. If you've not listened to Bruce before, I thoroughly recommend it. And on the 1st of July, Clive Davenhall will be going in the past again to review the Ludmark panorama. If you don't know what it is, I'll let you Google it. And Mark will be giving a scope talk. And on the 3rd of July, we've got the BioRock experiment by Dr. Rosa Santamarino. And I just perhaps ought to mention on the 17th of July, we've now got Dr. David Waltham of the University of London, who's going to give us a talk entitled, Is Earth Special? So I think we've got quite a good agenda, and there's a few more bits and pieces to fit in between. And with that, all I'll say is for questions, it's normal routine. For members, if you put them in the chat box, and Peter will monitor those. If you're looking on YouTube, put them in the comments section, and we'll try and get round to answering as many of those, or asking Hannah to answer as many of those as she can and as we have time for. So over to you, Mark. Thank you.
Okay, I'll stop sharing now, Hannah, if you want to start. So I'm delighted to introduce Dr. Hannah Wakeford of the University of Bristol to the Society. Thank you for being prepared to do this for us, Hannah. It's really kind of you. I first came across Hannah on the Exocast podcast. Everything you ever wanted to know about exoplanets every month, and it's really quite interesting and quite entertaining as well. So maybe Hannah will tell us a bit more about that, but they do have something which is a sort of a World Cup of exoplanets as well, amongst other things, which is great. And more recently, they went fishing for exoplanets. Interestingly, I also discovered that Hannah is the co-lead of the Stargate project, which must mean that exploring exoplanets is very easy when you can go through the Stargate to actually see them. So maybe you could tell us what that actually is. And possibly you can also tell us, is Earth special or not? But with that, I'll hand over to Hannah. So thank you very much, Hannah.
Yeah, thank you, Mark, and thank you so much for inviting me. I'm really excited to talk to everybody here and on YouTube. I don't know how many are on there. I'm not monitoring that right now. But I'm going to talk to you about exploring alien atmospheres. And this is something that I do and have been doing for a decade now. And I work with the Stargate Collaboration, which is a collaboration that uses space telescopes, and they're an advanced research group for the atmospheres of transiting exoplanets. So it's a perfect acronym, and it also works really nicely with what we do, which is exploring different planets. So to do that, I think what's really important is we start back at our own solar system. This is about alien atmospheres, and we have no shortage of those in our own solar system. And here's just a few of them. This isn't all of them. I really love all of these images because they show very different aspects of each of the planets. And we have this big question mark for planets beyond our own solar system. And I'm going to take you on a little journey to some of those and through our solar system and out beyond to try and understand how we're doing that, how we're exploring these atmospheres and what we might be learning about them. So I'm going to show you really to put things into perspective, and I'm going to keep doing that throughout this talk, our solar system to scale. You can see just the dynamic range of planet sizes that we've got there. And that really changes what it is that we're seeing and what they're made of. I really love this because it looks so clean. It looks so clean cut, but there is so many things that aren't clean cut about these atmospheres and how we're understanding them. And one of the things that we always need to remember is that we're actually planets that sit inside an atmosphere of our sun as well. So we are an atmosphere within an atmosphere, and that interaction is really important. These are some of my favorite images. I love the NASA SOHO images. They have this beautiful view of the sun where we can look at different mass ejections, so the particles coming out of the sun. And this is an image that I took whilst I was in Svalbard for my master's thesis. Of a solar substorm, of one of these events hitting our atmosphere and charging those particles. So we have to remember we're inside multiple atmospheres. The star is important as well. But to have an atmosphere, you need a little bit of gas. Gas is very important for our atmosphere. And even something like Mercury, which has what we call a transient atmosphere that is caused by the solar particles hitting the surface and kind of essentially sputtering off rock. So the rock is then being ejected in a gas is ejected from the rock and forms tiny pockets of atmosphere. And that's very, very low pressures. And you can see that diversity here. You can see that the pressures that we got on just even the small rocky planets, these terrestrial worlds, are very, very different. And then as we get to the gas giants, we kind of approximate it to a scale. Astronomers, even planetary scientists go, it's greater than 1,000. That's our approximation there. But you can see the huge range of different gases in those different colors that you've got there, the different combinations that you can use to make up a planetary atmosphere. And that means very, very different things for what we understand and what we can see in terms of those atmospheres. For Venus, one of the most hellish planets, very similar in size to the Earth, but has a very different atmosphere. It's got 90 times the amount of atmosphere as the Earth, all crushed into the same space. And you're seeing here an image from a Japanese satellite that is around there from the JAXA space agency. And what I love about this picture is you can really see the details of the atmosphere here, these sulfuric acid clouds. So if you were to go to Venus, go to the surface, you would literally be melted because of the temperature and the pressure. And you would be melted because of the acid. So it's not a nice place at all. And actually the Russian space agency landers, Venera, are the only things to reach the surface. But I'm hoping in a few years we'll get to go and really explore just how detailed these storm systems are on Venus. If we look at Mars, we also see an alien atmosphere. It's much, much thinner. In fact, a hurricane on Mars, the wind speeds might reach really high speeds, but the pressure is so low, you wouldn't even feel it. So you could stand in a hurricane force wind on Mars and you wouldn't even feel it. But what would happen is it would probably get pretty dusty. The material that forms the surface of Mars is incredibly small, thin particles. And this rust essentially would blow around you. And every time that Mars gets closest approach to the sun, there is this global dust storm that encompasses the planet. And that's due to the way the atmosphere is being heated up and the currents that exist in that atmosphere, just lifting all of that surface, all of that material and blowing it around. So you see this transition here from beautiful textured surfaces to this very, very blurry blob of red for Mars. And that's the dust being lifted up by its atmosphere. Now we need to move to our outer solar system a bit and to the king of all of the planets. and that is Jupiter. This is a beautiful image from the Juno spacecraft of the Great Red Spot on Jupiter. And it's actually 3 times the size of the Earth. It is huge. And it's even huge in terms of Jupiter itself. Jupiter, and this is a beautiful picture of the pole of Jupiter with all of those vortices that you can see there, is 11 times the radius of the Earth. So it's 11 times the size of our planet, but it's actually 317 times the mass. So its density and its structure are incredibly different. And as we saw before, it's mostly made of hydrogen and helium. So the 2 lightest, smallest elements compose a majority of Jupiter. And it's really, really, really dense in the middle. But we're trying to understand with the Juno spacecraft what the interior structure is like and what that means for what we're seeing on the surface. And the rotation period of Jupiter itself results in those banding structures you saw. So that banding structures that you can see if you get a telescope and you look at Jupiter, those are caused by the very fast rotation period. And we can use the information on this to try and understand what the banding structure might be like on other planets. Now, Saturn has, again, its own mysteries. The pole of Jupiter and the pole of Saturn look very different. This famous hexagon, and if we can zoom in and zoom in again, you can see these amazing high-resolution images from the Cassini spacecraft that was in orbit around Saturn for 13 years before it plunged into the atmosphere. And from here, you can see that natural structure that is formed from this wave that is being created by the rotation of the planet. And this, at the pole of the planet itself, you're seeing this very regular, strange structure. And that is just caused by the wave patterns that we've got. But at the center, this deep, intense storm, this massive hurricane that probes deep down into the atmosphere. So there's already this massive, massive range of information and things that we're seeing in our own solar system that is absolutely fascinating. And you can get these gorgeous, gorgeous images. But one of the most dramatic atmospheres in our solar system is actually Neptune. Neptune has the fastest winds in our solar system at 1,800 miles per hour. These whip around that planet so quickly, it's very difficult to imagine. But unfortunately, we've only had 1 mission to visit Neptune, and it was a very quick flyby. Actually, 2 months after I was born, this image was taken of Neptune from the Voyager 2 spacecraft. That was the last and only time we have seen Neptune up close. And I think it's high time we get another mission to go and take a look at these worlds and get those images like we've got for Juno and like we've got for Saturn from Cassini and, for Jupiter from Juno. We need that information for our Neptunes and our Uranus as well, so we can really understand the difference that the atmosphere is making. So we know that the atmosphere of Neptune and Uranus is composed of a little bit more of these other elements in them. They're not as much hydrogen and helium percentage as Saturn and Jupiter. And we don't really know what effect that might have and how that might change things. So there's so much we need to learn about these giants at the edge of our solar system, and we can actually get there, so we should. But this talk is about some really alien atmospheres, and to look at those, we need to go to the stars. We need to venture beyond the pull of the sun and go out into our galaxy and try and look at other stars. Try and find these planets that orbit them. Now, I think it's important here to kind of look at the history of searching for different planets from the one that we live on, from the ones that we see in the night sky or in our own solar system. And this thought process that we weren't the only planet to exist actually started in 450 BC with Epicurus. His philosophy centered around the fact that the Earth was not unique. We are one of many. And actually, if you look at Epicurean philosophy now, it seems a little bit doom and gloom. Nothing is unique. We are all one tiny little thing in a sea of loads of planets. But I think that that's really beautiful. I think that the fact that we are one of so much variety and so many interesting things in our universe, that we've got a lot of surprises ahead of us. But it wasn't until the 1600s that the thought of actually looking for these worlds kind of came about. And this is work that was published posthumously from Christian Huygens, a Dutch astronomer, and he postulated that if you look at a star, similar to the way that we look at Jupiter, and you watch it and you can measure then the movement that the planets have around that star, as we do when we see the moons orbiting Jupiter. So he actually thought of a number of different methods that we use now. We can look at these stars and see those planets in the same way we would look and see the moons. Unfortunately for him, we had no idea back in the 1600s how far away the stars were and just how difficult that task would be. And another thing that I like to point out is that the first exoplanet was discovered in the early 90s, but the first false claim of an exoplanet discovery actually happened in 1855 by W.S. Jacob at the Madras Observatory. He said that he had discovered a planet orbiting 70 Ophiuchi, and that was very quickly shown to be not true, but it is the first recorded claim of discovery of a planet. So this has taken 150 years to actually get from the first claim of observing a planet up to the discovery of a planet. And since all of this history, since 450 BC, we have for the last 2 decades been chugging away at this problem and actually discovering over 4,000 worlds, 4,000 planets beyond our solar system orbiting other stars. And what I'm showing you here is the distribution of those planets in terms of their distance from their star and the mass of that planet. So what you're seeing here, we can then compare to our solar system. And you can see when I put our solar system planets on there, it doesn't quite match up. And a lot of that is to do with the way that we make these observations. It's much, much easier for us as observers to find planets that are very close to their star, as you're seeing here, in many cases 20 times closer to their stars than we are to the sun, and to look for bigger planets. So the bigger the planets, the larger the influence they have on our measurements, and we can see them. The closer to the stars, the more times they orbit, and the more times they orbit, the more times we can get those measurements. So it's really an observational bias right now that populates this diagram in this way. But what's really important is that there's so many of them. And we're trying to understand how that relates to our solar system. How does that put our solar system into context? So to get an idea of the size of these planets and what they're like, I want you to imagine that the Earth is the size of a pea. So most of us sitting somewhere near our kitchens for the last 3 months, you've got to have an idea of different fruits and things around the house. So imagine the Earth is the size of a pea. Now, on this scale, Neptune and Uranus would actually be about the size of a plum. So they're not much bigger. They're 3.8 to 4 times the size of the Earth. Then Jupiter would be an orange, a nice round orange. And on this scale, most of these planets that we're looking at, and very much the early planets that were being discovered that sit above this line, you have to think of like a melon. So they're much, much larger in their sizes. And this is due to a number of different reasons that we're trying to understand. One being a number of them are very close to their star, so they're probably heated up and inflated, or they're younger, they've got internal heat, or different ways that they had to form and move through their solar systems to get so close to their star could mean that they're causing them to be puffy. So one of the things that we want to actually do is look at them in terms of their density. And I'm going to take these 4,000 exoplanets, and I'm actually going to whittle them down. I'm going to take out some of them where we can't get a measurement based on their radius and their mass. So now if we take out all the planets where we can only understand one of those two things, we end up with around 300 planets where we know both the radius of the planet and the mass of the planet, so we can work out roughly what the density would be like for these worlds. So we're down to about 300 of these, and I'm showing you them in two different ways. One that matches what I showed you before in terms of their distance from their star and their size, and one which puts this in terms of density. So the size of the planet, the mass versus the radius of the planet. And you can see where our solar system planets fit in there. And one of the things that links all of these 300 worlds is that they have all been measured using the transit method. Now, the transit method, as in that tiny little diagram up there, is when we measure the planet passing in front of the star from our point of view on the Earth. So if you're looking at a star and a planet is orbiting around it, if it's within a certain angle, a certain number of tilts of degrees, you will see that planet pass in front of the star's disk, and you can measure the change in light that causes. So imagine looking at a light and a bug flying in front of it. That light will get a tiny bit dimmer. In fact, roughly 1% dimmer. And we can measure that amount of light being blocked out and determine then, based on the size of the star that is assumed to be known, we can work out then what the size of the planet is. And if we measure it multiple times, we can work out what the period of the planet, so the orbital distance from that star, that planet is. So these worlds are really, really useful for us. So I'm going to be talking about some of these 300 worlds and using this transit method and how we start to try and pick apart their atmospheres. So we can look here as our fruit basket of planets and pick some of those to have a look at. Now, there are a number of different ways that we can look at these atmospheres. One of them is through emission spectroscopy. This is where we're measuring light directly from the planet itself, so light given off by the planet. And we can do that as the planet is about to pass behind the star. So when the planet is passing behind the star, the only light we're seeing is from the star itself. That gets us that continuous spectrum that you can see at the top there. Just before and after the planet passes behind the star, is blocked by the star, you're getting the star's light plus the planet's light. So from that, you can work out what light is coming directly from the planet itself. But the most common method that I'm going to talk about for the rest of this talk is the absorption spectrum, or what we call the transmission spectrum. And this is when the planet passes in front of the star from our point of view. Some of that starlight actually shines through the atmosphere of the planet before it reaches us. And as it's passing through that atmosphere, the atmosphere itself, what makes up the atmosphere, is actually absorbing some of that light. And because different molecules and atoms have their own unique fingerprints, they have their own unique signatures in light, we can actually try and work out what's in that atmosphere based on those absorption signatures. So just to show you how that works a little bit, I've got a little cartoon that I've made to try and illustrate that point. So we've got our planet as it passes in front of the star, and we can measure how big that dip is. How big is that dimming effect? So let's measure that. We've got a line that tells us how big that dimming effect is. Now, let's say we look over a very specific color. Say we look in the blue. We can now measure that dip again at that very specific wavelength. And we can keep doing this for a number of different wavelengths. And we can build up an understanding of how, with different colors, with different wavelengths, what the spectrum of the planet's atmosphere looks like. And we can then use our models to try and understand what is in that planetary atmosphere. Now, what you'll see here is the effect that measuring that dimming has on what we say for the spectrum. So normally, if you see a spectrum, you'd see a dip, an absorption, but we actually flip that up. So you'll see that our absorption signatures get bigger. And that's because the planet itself appears to be bigger because it's absorbing that light. So all of the spectra that you see from exoplanets compared to spectra you might remember playing with or have played with in the lab, absorption spectra are flipped because what we're measuring is the amount it's blocking out. And I'll show you a number of different spectra that we've got. And this is just one of the spectra that we've got, which shows you the sodium absorption in the atmosphere, potassium. So these are the atomic lines that we see in the optical. the absorption signatures of water vapor in these planetary atmospheres. Lots of water mixed in the atmosphere. And we know that Jupiter, Saturn, Uranus, and Neptune also have lots of water mixed in their atmospheres. And we're able to measure these different things, which is really, really exciting. So again, to show you just another way of thinking about that so that you can see that these are flipped around, is the change in the size of the planet itself. As that material in the atmosphere is absorbing it, it looks bigger. And as you go outside of those spectral features, it looks smaller. So it's really this change in size that we're able to measure. And we've done that for nearly 50 planets now. And less than 2 years ago, I couldn't have said that number. It would have been half that less than 2 years ago. We're really moving very rapidly to try and understand these worlds. And if I put it back on that diagram of the planetary mass versus planetary radius, you can see we're spanning this huge distribution from the smallest planets, the famous TRAPPIST-1 planetary system that you might have heard of. We've now measured 6 out of 7 of those worlds and tried to understand their atmospheres, all the way up to some of these largest planets that we're able to measure. And there's a huge amount more that we'll be able to measure in the future. One of the biggest studies that I was part of, this kind of composed my entire PhD, is a figure here where we're looking at 10 specific giant planets. And you can see the little graphic that we've got there of them slowly spinning, slowly rotating. And the big, big bands around the equator due to this slow rotation. I said before that Jupiter rotates really quickly and results in these lots and lots of bands on it. These planets actually are tidally locked. So they have a permanent day side and a permanent night side. That also means that their rotation period matches their orbital period. And these are orbiting their star on a period of days to about 1 to 5 days, I'd say, in this diagram. So they're really close to their star. These are not anything like in our solar system. These are truly alien planets. They are incredibly hot on their day side, going up to temperatures over 2000 degrees. And their night side is permanently shielded from that day side. So it gets much, much colder as you go around the planet. So there's really interesting things we've learned here. What I'm showing you here is those planets put in order, going from clear atmospheres where you can see those beautiful H2O features, those nice water bumps, some sodium and potassium, down to these flat and then really sloped ones. And from this, we concluded that there were clouds, there were things in this atmosphere interacting with the light in very different ways. And when we look collectively over a huge group of planets, so this is looking at 37 different planets, we're actually able to see that these clouds are affecting a large number of these worlds in very, very similar ways. So compared to what we expected to measure, we're measuring things that are muted to around 33% of what we would expect to see. And that's the clouds playing a role in there. Now, I want to kind of explore that a little bit further and see how we can work that out. And we can do that by looking at a spectrum. So I'm just showing you a typical model that we would expect for one of these planetary atmospheres. And I've labeled some of the different features on there that we would expect to measure. Now, if we put a cloud in that atmosphere and we measured that with these bands that I'm showing you here, these are the typical places where we are able to measure them. You can see that the clouds themselves will have an effect on what we're measuring. They look different. That spectrum looks different. Now, the green one here that I'm showing you is looking at clouds with large particle sizes. So these are things that are forming very large droplets or large things in the atmosphere, which is bigger than a micron in size. If we look at small particles in the atmosphere, then you can see a very different effect. You can see that slope instead of that flatness like we saw in that big 10 Jupiter study. And if we zoom in on just one of these features where we've got lots of information, we've got lots of observations at these wavelengths, we can see the difference between what we expect to see if there weren't clouds in the atmosphere compared to what we actually measure from those clouds being present in the atmosphere. So it's a really good explanation of what it is that we're measuring and what it is that we're seeing here. Now, go back to all of these different features and what can we learn from it? What can we interpret from these? And I'm going to do that liberally, if you don't mind. So let's explore some of these alien worlds and try and get an idea of what it might be like there. The first place we're going to go looks fairly similar to the sunset on the Earth. What you're seeing here is a simulation of a sunset as viewed through the atmosphere of a giant planet. But now what I'm showing you is it to scale with the Earth's sunset. First, you'll see a number of differences. One, the size. That's simply because we're so much closer to our star. We are on a giant planet orbiting in just 1.5 days around a star. And you're seeing actually all of the colors of the sunset at once. And you can do that because you're looking through that much atmosphere and you're looking at a star which occupies just a huge portion of the sky. And what that looks like in our measurements is very much like this, a very large slope. And this is very akin to our Rayleigh scattering that we get from the Earth's atmosphere, which causes the atmosphere to look blue. This is a very similar thing that we have measured for this giant exoplanet. So from this world, you wouldn't really see much difference in your sunset apart from the size of your star and all of the colors at once. But what is making this large scattering slope is very dangerous. The atmosphere, the beautiful blue atmosphere of HD 189733b is filled with violence, unfortunately. The star itself chucks energetic particles at this planetary atmosphere and blows off huge portions of it, as you can see in this simulated video. Huge parts of the hydrogen envelope of this world are escaping away. And the thing causing the slope that we're seeing is very small submicron sized particles of glass in the atmosphere forming clouds. So in Scotland, when you've been out and you've been standing in the rain and it's coming at you horizontally and it's whipping around, imagine those being molten glass flying at you, and you will get a good idea, if a cold one, of what it is like on HT 189733b. So while it looks serene and lovely, it is not a place that I would recommend you visit on your holidays. Now, another one that I really like, this is one of my favorite worlds, and it has the dullest of sunsets. It is a film noir sunset. We add a nice grayscale filter on there for you. Just get the cocktails out and sit back. But it's got a strange atmosphere as well. Instead of a slope, what we see is it is essentially flat. And what is causing this flatness is very strange. This planet has a dayside temperature of 2,500 degrees. Now, at that temperature, absolutely everything should be in the gas phase. It should be a vapor. Everything is vaporized at that temperature. So what could these clouds be made of? Well, what we think is happening here is that the heat is not being transported to the night side of the planet. And as it gets to the night side, it gets colder. Now, the first thing that will start condensing, will start forming these droplets to form this cloud at those temperatures, is something called corundum. And for those of you that might know, corundum is actually the basis of rubies and sapphires. So the clouds that are causing this beautiful grayscale, scattering the light in all different directions in the atmosphere of this world, are most likely made up of the aluminium oxide corundum, which, as we can see from here, some beautiful colors in there. We might want to go sieving for those, but remember, these are at temperatures over 2,000 degrees on a giant planet. So we're going to have to pack some very, very good spacesuits for this one. Actually, we're going to have to pack something that we haven't invented yet because everything's going to melt. And I want to kind of show again, back to this diagram, back to what we're doing from the theory side to try and understand this, is looking at these different simple models and going, okay, if we form a cloud and we make it out of small particles, what will that look like? And actually, if we look at some of these materials like glass, which is a magnesium silicate, you can also think of it as sand. So just common sand in the atmospheres of these worlds. And if we then kind of model and try and understand what they will do to the light, we can get an idea of how we're going to be able to measure them and what they'll be doing. And you can see here that we can match the spectra really, really well with these different particles. And what we're trying to do is understand how we can use that information to measure even more. So right now, we're very much restricted to the optical and very near infrared part of the spectrum with our measurements with the Hubble Space Telescope. But in the future, with the launch of the James Webb Space Telescope, we are hoping to be able to measure some of these clouds and their absorption signatures directly. So we can actually tell you, yes, this is a corundum cloud. Yes, this is glass whipping around, rather than us going, well, this is our best guess based on all of the physics and chemistry that we understand. So I'm really looking forward to the future for that one. And one of the things that we've recently done is we've looked at that collection of planets that I showed you. And this is work done with Peter Gow, one of my collaborators, looking at what kinds of clouds we might expect and which ones will be affecting the atmosphere. And as you can see here, it's those glass clouds, those magnesium silicates that are really dominant. We really expect them to be abundant. And that's because magnesium and silicon are everywhere. So they will form lots of material and we expect them to be lofted up. But you can also see those ruby and sapphire clouds, that Al2O3, that corundum. So I'm most excited about that portion of the spectrum. I wonder why, but it is going to be really exciting in the future trying to measure these. And again, just to tell you how strange and ridiculous these are truly exotic clouds. The coldest temperature clouds we look at, which is around 1000 degrees, is salt, just pure table salt forming a cloud in the atmosphere. Things that are yellow and crunchy, up to our rocky translucent gems, are different olivines. So this is a big bright green color when it forms crystals, and up to just a huge variety of different gems and jewels that form here on the Earth. They're the basis of all of the different materials that we expect to see in these planetary atmospheres, which is really exciting for me. As a trying to understand geology, I had to learn a huge amount of terminology that I had never heard of before in astrophysics. But I want to end on a little stranger sunset. And I want to end on this because I'm trying to emphasize that just the smallest things can make a big difference. And we should all be trying to do the smallest things to make the biggest difference. And you see this truly alien sunset here, this beautiful green to blue hue. And that is all due to this one little blip you see in that spectrum. That one little blip is sodium. That sodium is absorbing all of the orange light. It's taking it out and leaving you with this very nice filtered sunset from this planet. And I think that that's a really nice point, that just these tiny little things can change the way we view the world. And what we're trying to do desperately, this is the first time that I've put together this figure for any kind of talk, is just compile every single bit of information we have about these alien worlds. I'm showing you 39 of them here. These are measurements that have been made by the scientific community. And we're trying to put together this big Rosetta Stone, this library that we can reference and go, we can start to try and understand what's happening here and really place our solar system into context. And there is a massive array of worlds out there. We don't know what they look like yet. We've got an idea for some of them where we've got these amazing measurements, and we can use the human eye and we can project what we would see if we're out there based on the things that we're measuring. But there's just this massive, massive array of worlds left to explore. And we're only just beginning with the technologies that we've got. So as we move into the future, you will see so many different changes in exoplanets and our understanding of our own place in the universe. And it sounds like in a few weeks, you're going to have a talk which will hopefully explore that a little bit as well. But if you are interested and if you liked what I was talking about and want to explore a little bit more, as Mark said, I am part of a podcast with two of my colleagues, Andrew Rushby and Hugh Osborne, and we talk about exoplanets 3 times a month. So if you want to know more about some of the strange things, some of the more mundane things, and just an idea of what the scientific community are doing, then please check out Exocast. But I will leave it there on a nice little tour away from our sun.
Thank you, Hannah.
Brilliant.
A truly brilliantly clear exposition
Thank you.
of the topic.
We're still flying out there.
Oh yeah, we've got a long way to go.
Let us watch it.
I haven't quite finished yet.
What you're seeing there, those red dots, are all planets that we've discovered. And you can see, relative to where we are, where all of these planets that we're showing you we're talking about. You can see the direction throughout our galaxy, and that there's so much left to explore and so many things left to understand. So I'm very, very excited.
Wonderful.
Excellent.
Thank you very much. I say again, that was a very, very clear explanation and gave us a really good understanding of what's going on at the level we're at. So it's time for questions, and
Yes, we have a couple of questions here. Well, the first thing we had from Vincent was a nice statement about how well the president's doing, which I thought he must be after something. But, Sean, you had a question. Do you want to ask it yourself?
I will do. Yes, thanks very much. Thank you, Dr. Wakeford. That was a fantastic presentation, and you've a wonderfully entertaining presenting style, if I can say. It really kind of brings the subject to life. I was just curious about one of the big debates going on at the moment is how planetary systems evolve over time. There's a lot of recent discoveries about how our own planets have evolved, where they evolved very early on in the accretion disk around our sun when the sun was formed, and where they are now. And I'm just wondering, given we're now reaching maybe a critical mass of being able to study hundreds and thousands of exoplanets, depending on the type of parent star they orbit, what are we learning about how those various star systems evolve over time, and what happens to planets as their stars age, depending on their types of stars?
That's a really important question. And how and the demographics of planets. So not only planets that are the ones that I was talking about, which are often single planets around single stars, but planetary systems where we're finding 6 to 8 worlds, like the TRAPPIST planetary system with 7 planets around them. The demographics of those are hugely important in trying to understand formation processes. And what we know from quite a lot of these, they're very, very close to their stars. They likely didn't form there. So they likely formed much, much further out and then migrated through the system. So moved closer to their stars over time. And during this process, they could have destroyed or engulfed many other planets along the way and different things, or shot out other planets away from stars themselves. We know that there are free floating planets out there. So these are planets that are floating without a star. They're not orbiting anything. And these free floating planets are thought to be in their billions. So a recent estimate was that there are 5 billion free floating planets that don't have a star out there. And the result of that means that they got bumped away somehow. They got thrown out of their planetary system. So there's a lot of dynamics that happen there. And we know that from our own solar system, the heavy bombardment, the movement of Jupiter, the size of Mars can be explained by Jupiter coming in, taking some of the material and going out again. And a number of different things about the Kuiper Belt beyond Neptune and the understanding of those planets. So it's a really dynamic process to form a planet. And we're approaching these questions that you were asking from many different angles. One, from looking at these planetary atmospheres and trying to understand what they're made of and whether we can use what they're made of as markers for where they might have come from. We're looking at the demographics of solar systems, of different star systems, to try and see where planets are, how big they are, what distribution they have. And we're looking at disks as well. So actually planetary systems in the process of formation are really, really rich with details that we're trying to understand to fill in those gaps. And one of the planetary systems that actually got to the final of the Exo Cup, the Exo Cup is a knockout competition on Twitter, selecting the best exoplanet of that year. One of our runners-up last year, PDS 70, actually is in the process of forming these, and we can see 2 planets that are actually forming in those disks. So what we're trying to do from all of these different angles is build up that picture you were talking about, that there is this process, and whether or not that's a universal process is a really important question for us as a solar system. So I didn't answer your question at all, but I gave you lots of ways that we're trying to.
Well, it's an extremely good answer. Thank you very much.
Answer. Neil, would you like to ask your question?
Yes, absolutely. Yeah, thank you. That was a fascinating talk, really enjoyable. There seems to be a lot of project work that's dependent on the James Webb Space Telescope launching successfully next year. So I just wondered when you would start to see some usable data and how or where the exoplanet and exoplanet atmosphere projects fit in the queue.
So just to not put a damper on it, the James Webb Space Telescope was supposed to launch during my PhD. In fact, I started my PhD being told that I will be working on James Webb data by the end. That did not happen. That did not happen during my first postdoc, my second postdoc, and now I have my own PhD student, and we'll see what happens. But the amount of data that we have and the way that we're learning how to use that is ever changing. So that is not something that I would be worried about. But what your question was, when will we get that data and what will we get from it? So once the James Webb Space Telescope launches, it will take a month to get to its position. It will then unfold its little origami state. It is going to be folded up very neatly to fit in the rocket. And then it's going to undergo 6 months of calibration. So what they're going to do during that time is try and understand the telescope, make sure it's settled into its position thermally as well. So we've got to make sure that it's shielded from the sun. So one of the things that we've got to, you can see on the James Webb Space Telescope, that big sail-like looking thing, that is all cooling system. It's called a passive cooling. Because what is happening is the first one blocks the sun. Some of that heat's going to make it through. We can't help that. And then there's a second layer, and that blocks even more heat and even more and even more until the telescope, which is on the other side of that shield, is then so much colder, and we're able to run the instruments that we want. So it's going to take about 6 months to 8 months after the telescope has launched for us to start taking our scientific data. Now, in the first year of science, there are a number of programs that are going to be run. One set of those programs are called the Early Release Science Program, and those are community-driven programs where the community have put in different proposals to say, we want to do this as a group, as a collective. This is what we want to observe so that we can try and understand both the telescope and the science. And one of those is a exoplanet transiting community project to look at one of these giant planets that I showed you and see how all of the instruments are measuring it and whether or not we can understand how it's doing that. So within the first year, we will be getting that data, which I'm very much looking forward to, and always will be.
So fingers crossed for a successful launch next year then.
Yes. Very
Okay,
much
next
so.
one on the list is Will. You had a question, Will?
Yep, I'm unmuted. You mentioned about the glassy kind of debris which was taken, which would sort of be thrown away from a very close, large sort of supergiant planet to a star, and I was just wondering if there was any kind of link with that, with very small glassy chondrules which are found in meteorites. As far as I sort of understand, you know, with our solar system, as the sun formed, chondrules formed, and then you got the chondritic meteorites and stuff, which was all ended up being in our asteroid belt as debris. But I kind of wondered if there was like a star with a giant planet, and then the giant planet sort of formed near the star and then almost began to get vaporized. So you almost had a secondary thing of these glassy spheroids taken off it, if you see what I mean. I just wonder what your take on of that was.
Yeah, so what I was showing you there is actually not the glass being blown off, but the hydrogen and helium from the atmosphere being blown off. So the first things that's going to be blown off from planetary atmosphere are the lightest things. So the Earth itself has lost its hydrogen envelope. It's primordial. We had a very small amount of hydrogen that is being lost. We're losing helium, actually, at a significant rate from our atmosphere. So it's these lightest elements that are being blown off. But there is evidence for some other planets that are around hotter stars on very close orbits, so very dynamic and dramatic situations where we're seeing heavy metals being blown off. So before you get to the point where something like a magnesium silicate glass sand is being blown off, that's a very heavy material, even at its base atomic form. What will happen first is it will be vaporized. It will be vaporized into its constituent elements. So you get magnesium and silicon being blown off. Now, of course, silicon's much heavier than magnesium, so the magnesium will be blown off first. And we've actually seen evidence of magnesium and iron being blown off from these planetary atmospheres. And those are the things that we would really kind of be forming in these essentially clouds. And one of the big questions is, where does that cloud go afterwards? And would it be pulled into the sun, or would it form in a comet tail? And we've seen evidence of cometary-like tails of atmosphere behind worlds before, but the true composition of those is very much gas-based. So this hydrogen and helium. So I don't know about any secondary processes that can form that, but we do see in the interstellar medium, and like you said, in chondrules, we do see magnesium silicates in star-forming regions. We see evidence of these in large dusty clouds throughout our galaxy. So we know that they're out there in lots of different forms.
Marvelous. Thank you very much, Hannah.
Thank you for that. We have a question from Rosa. Would you like to ask your question, Rosa?
Yes, good evening. Thank you for this very nice talk. I really, really enjoyed that. My background is in biology, so it was very clear to me, and that's something that I really appreciate.
I'm glad.
And my question is more a curiosity. So I wonder whether it exists any way to infer or learn about the course of the exoplanets in some ways. I guess no, but I don't know.
Yeah, that's a really big, tough question that we wish we could answer, but that's something that we're really struggling to do in our own solar system. The best way to do that in any planetary system is to, if it's a gas giant, if it doesn't have a surface, gravity measurements, which is what Juno is doing. And the way Juno is measuring that for Jupiter is on a very eccentric orbit. So it's orbiting in a very strange way. And it's doing that because that's the best way to measure the very small changes in gravity around the planet. So the planet actually isn't perfectly spherical. The different bits on the interior of the planet are pulling that planet in different ways. So the gravity changes very slightly as you go around it. And the same's for the Earth. So the Earth's gravity isn't uniform. It bulges in very different places. The continents form a huge part of the differences in gravity on our own planet. So the best way for these kind of giant planets is to measure that. And for small planets or moons, so Titan, for example, is a really great, amazing dynamic world in our solar system with its own atmosphere. In fact, it's the only moon in our entire solar system with a very stable, thick atmosphere. And on something like Titan, you'd want to do seismology measurements. So Dragonfly, which is a mission that is currently being designed and built in America, will be going to Titan to try and measure the atmosphere and measure seismic activity. And that's really one of the things that we need to understand about these planets is the interior. And the only way we're really going to be able to do that is from our own solar system.
Thank you.
Thank you.
Nigel, we have a question from Nigel.
Yes, thank you very much, Hannah. That was a very enjoyable talk. I just wondered, I was looking at the names that these exoplanets had, which seemed to be rather long and involved. I just wondered whether there was an agreed convention internationally in the scientific community on naming of exoplanets, and how descriptive are the names of the planets in terms of whether they describe the size or the type of atmosphere or the distance from the star or whatever it is.
So the names of the planets are actually named in a couple of ways. For something like HD 189733, the planet itself is the little b at the end. So the b signifies the first planet in that system. and you can get C, D, E, F, G, H, I. We've found planetary systems all the way up to J. So they're the little sub letter at the end. Now, the first bit of the name is the name of the star, and that will change. So the name of the star, HD 189733, is actually from the Hipparchus catalogue. So that's a very old star. We can see it in the night sky with our telescopes and binoculars. It's very easy to spot, and it already had a name. So when a planet was found around that, it was just the name of the star plus a little b. Now, for something like WASP-12, that film noir world that I showed you, WASP-12 is the 12th planet that was discovered by the WASP survey. And WASP is a UK-run survey. They have telescopes in La Palma and Chile, and they actually surveyed as much of the sky as they possibly could to discover planets, and have now discovered over 140 planets. They are actually the most prolific ground-based survey for detecting exoplanets that transit their stars. So thank you to UK WASP Consortium for those. And those are named just in order of when they're found. And you can see that with most of the planets. So you'll see Kepler planets. Those planets will have been discovered by the Kepler Space Telescope. HAT planets were discovered by the HAT telescopes. So the description tells you what discovered it most of the time. It tells you what survey it was. And in some ways, if you know some of the nuances of those surveys, you can get an idea of what kind of category that planet might sit into.
Okay, thank you.
Thanks for that. Mark, is there any YouTube questions?
Oh, yes.
Oh, no.
I'll ask some of them. When you're performing spectroscopy on planets, is it necessary to correct for redshift in the wavelengths, or does that not affect that has any that matters really?
So we don't have to correct for that when we're measuring the spectrum of the atmosphere itself. But if you are measuring the radial velocity, so if you're measuring the mass of the planet itself, what you're actually measuring is the star, and you need to correct and understand that. So there's something that happens if a planet is transiting at the same time that you're measuring the pull of the star. You'll see the two hemispheres of the star in this Doppler effect. So one side will be red, one side will be blue, and you do have to correct for that then. But when we're measuring the atmospheres of these planets, we do not have to correct for Doppler in this.
Okay, we have a question from Ken Friedman. Can one evaluate the atmospheres of habitable zone planets for the spectra of chemicals that do not exist in nature on Earth? Maybe chlorofluorocarbons, an industrial footprint, perhaps?
Yes, so one of the kind of quibs we always make is that if we discover CFCs, so chlorofluorocarbons, in the atmosphere of any exoplanet, then we know that the people that live there are really stupid. So that really would be just like a massive indicator that there's something there producing artificial things. Those are really hard to measure. While they have a huge impact on our atmosphere, there's not very many of them. So to measure their spectral features, they would have to dominate over the spectral features of oxygen and ozone, and they'd have to dominate over CO2 and water. So you would still need a huge amount of these materials in the atmosphere for you to be able to measure them. So that's one of the really big challenges for looking at smaller terrestrial worlds, is their atmospheres are smaller. So if you compare the size, the depth of the atmosphere of Jupiter to the Earth, then you can just think about like how much harder it is to measure something that is passing through that atmosphere before it reaches our telescopes. So it's a challenge for us to really be able to do that. So what we're looking for is these dominant species. And one of the really nice things that we're looking for is carbon dioxide, methane. Methane and carbon dioxide are really nice indicators. But what is really important is how they are relative to each other. So how much of those materials are there relative to each other? Because nature likes things to be equal, in equilibrium. It likes a balance. And if something's out of balance, it has to be out of balance for a reason. So we're looking for reasons why these materials in the atmospheres might be out of balance. And from that, we might be able to learn something. But those measurements are a little bit away from us right now.
We also have one about these orphan planets. Are we able to study the atmospheres of these rogue planets? Because they can't be studied in relation to the stars.
So one of the things that we use for these rogue planets is we're only really able to measure them if they're still emitting their own light. So because they're not around a star, they're not getting any external heat. So we have to be able to measure their internal heat kind of breaking through, like coming out of them. And as a planet ages, it cools down. So what we're seeing for these rogue planets, the ones that we've been able to measure, are very, very young. So they are still emitting their own heat that we're able then to measure. And this is more akin to that emission spectrum that I talked about before, where if the planet goes behind the star, we're measuring the light directly from the planet. And that can tell us lots of different things. And we treat those more like something called a brown dwarf, which is a substellar object that hasn't burnt its own fuel. It hasn't burnt to become a star, but it's massive enough to have a huge internal heat. And the way we measure those is understanding the amount of heat that is able to escape and what we can measure in that. So these rogue planets are incredibly difficult to find, But from the numbers that have been found, they have been able to predict that there are billions of them out there.
Okay. We have one about infrared. When did you come up with the idea of using infrared, and what about using vibration modes?
So an excellent point. Infrared's been used in astronomy for many, many years. If you want to go to smaller stars, to colder things, you need to go to the infrared. So we're talking here about the black body spectrum, the spectrum of energy that something gives out. You and me give out a spectrum of energy, and where that spectrum peaks tells us what wavelength we need to look at. So the smaller, the colder that you go, the more into the infrared you need to go. Now, the point about the vibration modes is very, very good. That is some good inducing from them. What we're seeing with that big bump in the infrared from that cloud that I put on there, that big purple cloud and that nice big bump, that is actually the vibrational mode of the silicon and oxygen bond in sand, in that magnesium silicate. So what we want to do is we want to be looking for this main bond, which is the one that's vibrating between them. What we're measuring now is mostly rotational and vibro-rotational bands of water, CO2, and then the atomic bands of sodium and potassium. But we want to see the vibrational modes of these larger molecules and look at where they're going to absorb the light. And you do have to go to the infrared for that.
You're muted, Mark.
Sorry, there we go. Got children around, so it's going to be a bit noisier, sorry. Has your data ever indicated a possible habitable planet, and does your project work alongside the Kepler mission?
So the data that I'm doing looks at planets that have already been discovered. So some of the planets that we've looked at are from the Kepler mission, but the Kepler missions was set out to discover planets. And it was set out to discover planets so that we could understand the distribution of worlds out there and the number of worlds out there. So actually, you're seeing on this diagram a big spike that goes off to the left. That big spike that goes really deep, that's the Kepler mission. And that's because it's looking at stars that are very distant from us. And the more distant from us, the more difficult it is for us to study them. So actually, we haven't looked at a huge number of planets from the Kepler mission to look at their atmospheres because they're very difficult to follow up because they're very dim. The TESS mission that you might have heard of, the Transiting Exoplanet Survey Satellite, which is currently in orbit around the Earth, is looking at the whole sky for the brightest stars to find the best planets to follow up and study their atmospheres. So we're going to have thousands more planets that we're actually able to look at their atmospheres of and pump up that 300 planets to thousands in the future. And in terms of habitable zone worlds, so the habitable zone, for those that don't know, is a temperate region. So it is really like Goldilocks. It's the nice temperature from a star in which liquid water can form. So this forms kind of a boundary between the closest point to the star and the furthest point from the star. And the atmosphere of a planet can change that boundary a little bit. We can see that in our own solar system between Mars, Venus, and Earth. They're all in traditionally what would be called the habitable zone, but they're all very, very different. So there's a lot of variety inside that one definition that we need to be really careful of. But one of the things that we can look at with the TRAPPIST-1 planetary system, that's a really interesting system because there are 7 planets that are roughly the same size as each other. And they're actually roughly the same size as Venus and the Earth. So they kind of range between those 2 planets. And they actually go from inside, very close to the star, through the habitable zone of that star and out into the icy regions of that solar system. So by looking at those planets and understanding the atmospheres of those worlds, if they have any, will be a really good indicator for our understanding of this temperate region around a star. So in the future, we're hoping to be able to understand that a little bit more.
And one question must get asked quite a lot, given our natural curiosity and drive to discover things in exoplanets and other solar systems. How can that help us with the problems that we have on our own planet?
One of the things that I really hope it does is it makes us realize just how special our planet is. That's one of the things that we need to be reminded of far too often, that this is an incredibly special world and that we need to treat it that way. The atmosphere of our planet has just beautiful dances and dynamics. I love studying the weather of our own planet, the interaction it has with the sun, as you saw in that picture at the beginning of the aurora. That interaction alone tells us a huge amount about our planetary atmosphere. And trying to understand these worlds will really help us put into context our solar system. How special is it that we've got a giant Jupiter and then this string of giant planets and the terrestrial planets on the inside of all of that? How special is that? How important is that configuration that we've got? We actually haven't found a planetary system yet that looks like this, that looks like our solar system. Now, of course, I also showed you that we're not looking in the right place just yet. We don't have the right technology and techniques to be able to look in the right places just yet. But hopefully in the future, we're going to have missions that are able to measure more generically the different types of systems. And one of these measurements that can be made is through something called microlensing, where you can measure the mass of a planet just once, unfortunately, so we can't look at their atmospheres. But what you'll be able to do is measure things down to the size of Mars, out to the distance of Mars, Jupiter, Saturn. So hopefully we'll be able to fill in that diagram a bit more and really place our solar system in that context in the future. But there's a lot of things that we just need to think about as we're learning about the physics and chemistry, we can think about how our own planet has evolved through time. A lot of the stuff that astrobiologists do and a lot of the stuff that atmospheric scientists do is look at how the Earth has changed through time and what each of those stages has meant for us. And I think that's really important.
And I have one final question from my son, Robert, here, who's about to go and study physics after the summer at university. How does he get into this amazing stuff?
Just be interested in it. There will be people at your university that you're going to that will be interested in it, hopefully. I don't know where you're going, but I'd be happy if you wanted to contact me and discuss it a little bit more. But have an interest in something and go looking for things. If you ask people, asking people is the best way to get different projects. You'll be doing different projects throughout university degrees, especially in physics. There'll be lab projects. Get onto the ones that really inspire you to think about things. It's about deep thinking, and physics allows you to play around with that. So if you're interested in these kinds of things, go and do the courses that are on environmental physics. So learn about the atmosphere, learn about how an atmosphere moves and interacts with its environment around it. Go on the courses that learn about stars and what different stars mean in our galaxy, and just put all of those different pieces that you're going to learn together. That's what physics is, just putting all the puzzle pieces in one place.
It's as simple as that.
No, it's not as simple as that, unfortunately. I wish it was. There's so many puzzle pieces, and some of them have very sharp angles.
Thank you very much, Hannah. I'd like to say that we would like to send you a small speaker's gift. Don't get too excited. It's very low value, but some people have found it quite interesting. If you just email Mark or message Mark with your address, we'll arrange to have that sent.
Great, thank you
very much indeed. That was wonderful.
I'm glad.
Thank you.
Thank you.
Thanks.
Okay. Thank you very much, everybody. And I hope to see you on Friday.